Hello, welcome to today's class. In today's class, we will talk about parallel adder, and another name for it is Riipple carry adder. So, let's say we have a 3-bit number. So, there are 3 bits in that number, and we call the bits as A0, A1, and A2. And then we have another 3-bit number, and we call the 3 bits in the second number as B0, B1, and B2. So our first number is A and our second number is B, and we want to add these two 3-bit numbers. So basically we want to add the 3 bits A0, A1, A2 with the 3 bits B0, B1, B2. We have already seen how this addition can be performed in one of the earlier class. In that class we took the example of these two numbers. So let's say the first number A is 111, which means A0 is 1, A1 is 1, and A2 is 1. And the second number is 101, which means B0 is 1, B1 is 0, and B2 is 1. And we have seen how to perform the addition of these two numbers. First, we will perform the addition of the two least significant bits. So basically we will be adding A0 with B0, and since A0 is 1 and B0 is 1, we are performing the addition 1 plus 1, and 1 plus 1 we know is 10, and so 1 plus 1 is sum of 0 with a carry of 1, and this sum 0 we will write down as the sum from the first stage. So in the first stage we produce a sum of 0, and the first stage also creates a carry of 1, and this carry will be provided as an input to the second stage. So please remember this. What we are doing is, whatever is the carry out from the first stage, we will provide it as the carry in for the second stage. So now we will perform the addition of the second stage, and in the second stage we have to perform the addition of these 3 bits 110, and 1 plus 0 will actually produce you a sum of 0 with a carry of 1. So the second stage produce a sum of 0, and it produce a carry of 1, and this carry will be provided as a input to the third stage. So whatever was the carry out of the second stage, that carry out we provided as an input in the third stage. So now in the third stage we have to perform the addition of these 3 bits. So we have performed the addition of A2 and B2 along with the carry from the previous stage. So here A2 is 1, B2 is 1, and this one is the carry from the previous stage. And when we add 1 plus 1 plus 1, it will result in a sum of 1 and a carry of 1. So the sum produced in the third stage is 1, and the carry produced in the third stage is 1, which will be the final carry of this addition process. So this is how the addition of the two 3-bit numbers will proceed. And whenever we have to perform the addition of 3 bits, we have studied that this addition can be performed using a full adder. So full adder performs the addition of 3 bits, whereas a half adder performs the addition of only 2 bits. Now to perform this addition of the two 3-bit numbers, so this example shows how we can perform the addition of any two 3-bit numbers, A0, A1, A2 plus B0, B1, B2. And what we saw is that we can use one full adder to perform the addition in the first stage. So in the first stage, we have A0 is 1 and B0 is 1. So in the first stage, we are performing the addition of the two bits A0 and B0. And since we don't have a carry input, the carry in for the first stage, we can assume it to be 0. So this C0 will actually be equal to 0. Why? Because in the first stage we don't have any carry in. Now this full adder will have two outputs. One is the sum, the other one is the carry. We call the carry C1. And now the second stage of this addition of these two 3-bit numbers, the second stage, we can use another full adder to perform the addition of the second stage. And we have already seen that the carry out from the first stage is provided as a carry in to the second stage. So whatever is the carry out from the first stage, we can provide it as a carry in of the second full adder, and the two other bits of the second full adder will be A1 and B1, because we are adding the bits A1 and B1. So for the second full adder, the three inputs are A1, B1 and C1. And what is C1? C1 is the carry out from the first stage. And this full adder will also have two outputs. One is the sum, the other is the carry out. And now to perform the addition of the third stage, we can use the third full adder, and whatever was the carry out of the second stage, we are providing it as a carry in for the third stage. And in the third stage, we are performing the addition of the two bits A2 and B2. So the two other inputs to the third full adder is A2 and B2. And the two outputs of the full adder are S, the sum output, and the carry out. So this addition of these two 3-bit numbers can be performed by using three full adders, which are connected as shown in the above diagram. So inputs to the first full adder is A0, B0 along with 0. C0 should be equal to 0. The second full adder inputs are A1, B1 and whatever is the carry out from the first stage. And for the third full adder, the inputs are A2 and B2 and whatever is the carry out from the second stage. And this logic circuit is called a parallel adder or a ripple carry adder. Although it's very simple to understand the working of this parallel adder. However, it has a drawback because it is slow. And why is it slow? Is that if we look at the third stage cannot perform its computation until and unless the second stage has completed its addition. And why is it so? That's because the carry output of the second stage is provided as the carry in to the third stage. So until and unless the second stage is done computing the value of S1 and C2, and the full adder in the third stage cannot perform its computation. The full adder in the third stage can perform its computation only when C2 is available. And for C2 to be available, the full adder in the second stage should complete its work. Then only C2 will be available for the third stage. And now the full adder in the second stage cannot complete its computation until and unless the first stage full adder has completed, because only after the first stage full adder completes its addition that C1 will be available to the second stage full adder. So as you can see, if we are performing the addition of two 64-bit numbers, we will have 64 full adders connected in this way, and the 64th full adder will have to wait for all the previous 63 full adders to complete their computation. Only after that the 64th full adder will be able to do its computation, and it will take some time for this carry to go through up to the 64th stage full adder. So it is, and that's why it is slow. So that's the drawback of the 4-bit parallel adder, of the parallel adder. And there are alternate circuits available which can compute the addition in a faster, and those kind of circuits are called the Lookahead carry adders. In this class we are looking only at the parallel adder, and we have seen how it works, and I hope you have understood how it works. And now let us try to implement this logic circuit in Logisim. So here I have the full adder logic circuit, again which we have done in one of the previous class, and let us see how we can build the 3-bit parallel adder in Logisim. So first thing we will do is we will change this name, the name of the circuit. I'll click here and I will remove whatever is the current name, backspace, and then I will name it full adder. So when I change the name here, it also changes here, as you can see. So this is our full adder circuit. And now I will go to project and I'll say add circuit, and this time I will name it 3-bit parallel adder. So that's our new circuit. So now if I double click on this full adder, I'll see my full adder circuit, and if I double click on the 3-bit parallel adder, I will see the 3-bit parallel adder, but we have not built the logic circuit yet. We want to build it, and how we will do it. First, let us look at the full adder logic circuit. So I double click again, and let's see the inputs. So I have 3 inputs: X, Y, and C in, carry in, and I have 2 outputs, sum and carry out. So remember the order of these inputs, it's X, Y, and the carry in, and the order of the outputs is sum and then carry out. Then I go to my 3-bit parallel adder, then I click here, single click, not double click, and then I click here. So what I have here is now a full adder circuit. So I need, if you remember from our discussion on the theory class, to perform the addition of the 2 3-bit numbers, I need 3 full adders. So I have 1 full adder here, and I need 2 more full adders. So again I will click here, and then I click here. I click on full adder, single click only, and then I click here. So I have the 3 required full adders, and if you remember, the first input is X, the other one is Y, and the last one is carry in. And here in the output, the first output is sum, and the next output is carry out. Let me zoom it a little bit. Okay, I think this is better. And now if you remember, the carry out from the first stage should be provided as carry in of the second stage, and the carry out from the second stage should be provided as input, as a carry in input of the third stage. And now for the now we are trying to add 2 3-bit numbers. So the first number had 3 inputs, 3 bits, A0, A1 and A2, and the second number had 3 bits, B0, B1 and B2. So total we have 6 bits. It would be difficult or it would be cumbersome to have 6 inputs like this and then connect it. It's possible, but as we increase the number of bits, if we try for example 2 8-bit numbers, then I will have 16 inputs, 8 inputs for the first number, 8 inputs for the second number, total 16 bits, and it will be a little bit complicated to put all the inputs. So instead what we will do, we will go to this wiring section. I'll click on the wiring, and there we have something called a splitter. So I'll click on the splitter and I'll put it here. So in our case we need 3 bits. So here in the fan out I will put 3, and bit width I will put it 3, 3, 3, and then I can make it face south, and now I can connect my input, and as I connect it is showing some error. That's because here the data bits is 1. our data bits actually is 3, so I'll change it to 3. So that gives us the first 3 bits. That gives us the so this is our A0, A1 and A2, and then we need B0, B1 and B2. So for that I'll take another splitter. Again it should be 3 bits and 3 bits. I'll make it face south and I'll put it here, and I need the input, so I'll put it here. I'll connect it here. It'll give you error, so I change it to 3, and then I have B0, B1 and B2 also. So A0, A1, A2, B0, B1, B2. And let me pull these wires. I am just pulling the wires, making it make it easier to make the connections. And okay, here we go. So if you remember, the first stage I should add A0 and B0. In the second stage I should add A1, so this is A1 with B1, so this is B1. And in the third stage I should connect A2 with B2. Okay, so I have connected all the inputs except this one input, which is the carry in of the first stage. And if you remember from our discussion, in the first stage this should be equal to 0. So for that I take a constant and I put it here, and the constant should actually be 0. So I change the value to 0. I first remove backspace and then I write 0. Okay, it should be 0x0. Yes. So if you just put 0, it will be error. So you make it 0x hexadecimal 0. And then I need to connect this 0 to this input. So the connections are done. Now I have to take the outputs. So for taking the output, I will again use a splitter, and this time the splitter should be facing the other direction. So I put it west, and this output I have 3 sum bits, so I'll call it 3 3, and so this is your sum 0, this is sum 1, and this will be your sum 2. So now I need to look at the output, so I'll put the output here and I'll connect it here. That will give us error, so data bits I need to change to 3. Okay, there you go. And now this is my sum 0, so I connect it to 0, and this is my sum 1, so I connect it here, and this is my sum 2, so I connect it here, and now this is my final carry out. So I connect it here. So that completes the connections, all the connections. Now we can try to verify by performing some additions. So let's say I want to perform the addition of these two numbers, 000 and 001. And if you perform this addition, it should be 001 and carry out will be 0. So it looks correct. So let me change this bit also 1. So now 1 plus 1 will be 0 and this bit should be 1. So sum should be 0, 1, 0 with carry out 0. So let me change this to 1. Yes, I'm getting the correct output, 0, 1, 0. And now let me change this to 2. So this is 2 plus 1, it should be 3. And yes, I'm getting the output 3. Let me make it 5. So let me make it 5 plus 2. 5 plus 2 should be 7. So if I change this bit to 1, I should get 1, 1, 1 here. So let me change this bit to 1. Yeah, I'm getting 1, 1, 1 as the 7. So 5 plus 2 is 7. So like this, you can test your logic circuit. So what we have done today is we have built a logic circuit which can perform the addition of two 3-bit numbers. And to perform the addition of the two 3-bit numbers, we have used 3 full adders, and the connections are as was discussed in the theory class. And this kind of a logic circuit is called a parallel adder or a ripple carry adder. And this is actually a 3-bit parallel adder or a 3-bit ripple carry adder. So with that, I would like to end today's class. We will meet again in the next class. Thank you. Bye.